roles before moving on to technical leadership roles with Network Rail headquarters. Left Network Rail in January 2012, and between then and September 2019 was effectively the technical authority for all track engineering matters at HS2, developing their strategy for the track system, most notably the specification of slab track as the predominant track form between London and Crewe. I'm sure we'll hear more on that as the evening progresses. So just over 3 years ago, Niall moved back to Network Rail as head of engineering in his current role, working within the Eastern Region Capital Delivery team. So I'll hand over to Niall. Thank you very much for coming along.
Thank you very much. Good evening, ladies and gentlemen, and people online. I'll start with a few qualifications. As Ben said, I left High Speed 2 in 2019, so some of the details that I show here could well be superseded at this stage, but the focus should be on engineering principles. That's what I want to talk about, as opposed to just the specifics. So the second thing is I'm going to be somewhat challenging in terms of I'm going to make certain statements. Now, you may agree with them or you may not. It's not personal. Don't be insulted or don't get angry. You know, if I am irreverent, I was so hoping I wasn't going to say irrelevant, but irreverent to your institution, department, company, industry, fine, come back at me. The whole point of this is if I say something you either don't agree with or you have an alternative view, you know, please ask the question. Ben is going to handle the questions from online, is that correct? Or Louise? Okay. So, and as I said, some of the things I say, my tongue might be in my cheek or it may not. So, and finally, some of you will have seen some of the slides I've had. Well, most of the slides I've done previously anyway, but more recently at our engineering conference up here in York in October, I've put in a few slides because again, it deals with the principles and in terms of where I think we are in terms of engineering in this day and age. So the need for engineering excellence. Okay, now that's as good as my graphics get, by the way, that little moving pound sign. But again, we've had, you know, we've had political upheaval like last year, like we've never known. We've had, again, at the time, there was a £60 billion black hole, which is what that's supposed to be up there in terms of cash. We were downgraded, you know, the economic outlook was downgraded from stable to negative. I don't know where it is now, whether it's, you know, 6 months later, whether it's come back up again, but you get the idea. There's a lot of political uncertainty. And of course, we have the cost of living crisis. As it's known, we have the war in Ukraine, which is affecting it, which is affecting gas prices. And personally, my utilities went, I think, from November, December and January, mine went from about £250 a month to 300 and something to 426, even though I spent nearly a month away in December in the Far East. So, you know, which I have to say shocked the hell out of me. So it just gives you some kind of idea. So what has that got to do with engineering? Well, I actually think it's got everything to do with engineering. So what can engineers do? Now, for those of you who like Dilbert, I think Rich probably can't see it there, but basically it says that managers are supposed to be dumb and engineers are supposed to be smart. Okay, and you know, in a nutshell. So I think what we're here to do is to question, to challenge, to understand, to reason, to produce. As engineers, that's what we should be doing. We should be using engineering principles to challenge practices, engineering standards. And I've got at the end, can you make a career out of following process? Well, unfortunately, yes, because I think we've bred a generation of engineers who tick the box, follow the process. And it's not their fault because that's how we've beaten it into them, I think, over the last 10, 20 years, you know, you know, follow the standard, follow the process. And I think whilst we need processes and clearly we need standards, I think how we kind of interact with them should change. So what I'll cover this evening. So I'm going to do a bit about HS2's approach to specification and design. And the key word is approach here. Potential failure mechanisms of track, because I think that's really important. And when you're comparing high-speed rail to conventional rail, well, failure mechanisms occur, shall we say, and a lot of them are very similar, if not the same. How we challenge and improve, i.e. learning from good practice, but for also bad practice, failures. That's really important. And again, that's one of the things I put into practice in High-Speed 2. So what that looks like in a bit more detail is I'm going to cover track system design. Now, track system design is something we very rarely do in the UK, because if you think about it, when we actually design track, we actually don't design it. So track renewals, what do? We look up 2102, track category, and it basically tells us there's a table that says Sen 60 rails, G44 sleepers, 300 mil of ballast. There's no design. You know, what loading's going into that? What's the stiffness of the pads that come with the G44 sleepers? Does anyone know? I would suggest most people don't. So we tend not to do track system design. When you have slab track or ballastless track, you have to design it. Track alignment, which is the key thing now at the moment. We're challenging lots of track alignment standards, middle and main line electrification, or TRU here, because we have a lot of bridges where we are electrifying non-electrified routes. If we're not careful, it could become very expensive in terms of bridge reconstructions. So what can we do in terms of challenging the standards for both the electrification and the track? And it's a system design. Sorry, I keep going like that. Systems design, rolling stock, track, and a support platform. So, and I'll cover S&C briefly and the track support platform. And I've just added at the end. So even though this is my experience in high speed, I got involved in a few workshops recently about the 140-mile-an-hour running, potentially on the East Coast Main Line. So this is very relevant. So this may come to somewhere near you soon. So client-led specification and design. I'm very keen, or well, I'm a believer in, as a client organization, we've got to lead, okay? And what I mean by that is we've got to take ownership. I think it's really important. Now, I've seen, again, when I was with HS2, we were speaking to a lot of other infrastructure managers. And in Sweden, for example, when I got talking to the guys who were they were in the development stage. And when I got talking to them, I said, oh, so how are you choosing your track form? Oh, we're going to let the contractor decide. Okay, right. And everything was, oh, well, we'll just put it in the contract. The contractor will, decide. I personally don't agree with that, because contractors price risk. Because one of the first things I learned as an engineer, contractors price risk. I think the really clever bit is, as a client, is to know what risk you keep yourself and what risk you give away. And it's finding that sweet spot between them. So it's about ownership for me. And in HS2, we did that. Ben mentioned the technical authority. Well, that's what Andrew McNaughton called us. He termed that, and he developed that term for the team, his team in HS2, which was the technical authority, which has since been adopted by Network Rail. So client organization, what should it do?
I'm just going to take a photo while you're talking. Just so
okay. So own the vision and strategy. I think that's really important. That's got to, and the risks. So that's really important as a client organization. I don't believe you can just farm them off, because it'll come back to bite you. So what we did as well, so we basically collaborated with high-speed partners, because what's the point in trying to reinvent the wheel? So luckily for me, I spent an awful lot of time in Europe, and I even got as far as Japan. And there's a photograph from inside a cab of Shinkansen that I took, which I'll show you afterwards. And but we wanted to find out what is best practice? What do other people do? And the interesting thing about High-Speed 2 is, whilst I won't say in engineering terms it was a blank sheet of paper, because in the UK nothing's ever a blank sheet of paper, but it was probably as close to a blank sheet of paper as we're likely to get. HS1 doesn't really count in my view, because HS1 was an old French design bought off the shelf, and I'll show I'll make reference to that as well. So we did a lot of workshops, investigations. We commissioned reports, cost a fortune. You wouldn't believe. And some of those, so on the top right, we got a sister to do 2 reports, and that was fundamental in terms of us developing the evidence to go with slab track, because it allowed us, and I'll go into this in a bit more detail later on. To the left of that is a report from the Technical University of Graz, which is a guy called Professor Peter Veit. And if you Google him, you'll find loads of presentations about whole life costs, track, undersleeper pads in particular. So we went to him for undersleeper pads. And the bottom right is reports done by J.R. East, Japan. And as I said, I was lucky enough to go to Japan as guests of J.R. East. I have to say, and this is just an observation, when I was over there, it was fabulous. But their track isn't very good, I have to say. I think they've spent, to me, it was apparent that they spent the last 20 years putting all their technological know-how into their rolling stock rather than the track, because the track had changed very little in 20, 30 odd years. So, but again, that's just an opinion. So we wanted to incorporate best practice from around the world, but also likely failure modes. And I'm going to talk about 053 for those of you, prevention of derailments at facing switches. So if any of you have a maintenance background, that's a big thing. And of course, there was a point some years ago when the majority of passenger rolling stock derailments, I'm just getting this right, occurred at low speed on sets of, on facing switches. So we've had a lot of them over the years. And of course, we carried out modeling to inform early design as well, which was really important. So specifying for a successful outcome. So in that vein, right, well, this is easy, isn't it? Just, you know, just issue technical specifications, the designers design, the constructors construct, and then we put it into operations. Easy. What could be simpler? Well, of course, that's not the case. We have to, the first thing we need is requirements, an operational strategy and requirements. And I have to say, if anyone's here from the route teams and the sponsors, we are rubbish at requirements. We're absolute rubbish at requirements in Network Rail. And if you, as capital delivery, and I've been on the other side, as Ben said, I was maintenance, and a lot of my career is maintenance, the first half of my career. But we tend to dabble. I think you might need to ask this. There's a train coming, or no, it's a Hoover. So we tend to, I think, you know, the maintainers, the RAM teams tend to dabble with designs, they sign things off. I think we've really got to focus on requirements. It's really important. So that's the first thing. And of course, constraints. And in terms of building a new railway, High Speed 2 was a new railway, and you've got the UK, and I'll go on about track alignment standards afterwards, but ultimately we're a small country. The UK is not a country. England is a small country, because that's we haven't made it as far as Scotland yet, and I don't think we're going to Wales. So, but I could be wrong there. But anyway, but the point is, it's a very congested, high density country, and therefore the constraints that we have to live with are different compared to France, Germany, or Spain, which are generally huge countries in comparison. So, and that makes a difference to your standards and specifications. So, as I said, we did a lot of client-led early designs and investigations to inform our specifications. So design has to be about, should be about high availability as well. Availability means in this context that very few possessions for maintenance, but we do need to have some as well. Quality. When we talk about quality, I think most people think about construction quality, but it's also design quality. It's the quality of the design. And I don't mean mistakes per se. It's actually good design versus a compliant design. And again, I'll cover that as well. And of course, there's the asset management, how we're going to manage it, especially with remote condition monitoring, infrastructure, monitoring trains, automated train-borne inspections. It's really important that we think about that during the specification and design stage, as well as the construction. And if we do that, well, then we have a chance of getting into operations. And I'll put a circle there because reliability is key in a brand new railway. If I mean, I have no idea when HS2 is going to open, but when it does, can you imagine if there's a points failure on the first day, you know, after taking how many billions, you know, it's just unthinkable. And therefore, so reliability will lead to customer satisfaction, of course. That will improve the reputation, because reputation is hard to build up, but it's very easy to crash. And that applies to every one of us in this industry. And that leads to the business case. So the key point, and I think, going back to my comments about risk, this is one of the ways I think as a client organization, you manage your risks, if that makes sense. So railway is a complex technical system. Train, track, support structure, earthworks, got vibration control systems, you mentioned control systems. just for Dermot.
Thank you.
So it was worth you coming. So noise, and in the middle I've got the track because that's the center of the universe. Quite literally, the track's the center of the universe, and but it's really important. But so there's multiple interfaces. So what goes into that? Is where I'll try my thing. So firstly, I'll see what I'm doing. Operating conditions. So how many trains per hour is really important. If you've got 2 trains an hour as opposed to 18 trains an hour, there's a big difference in terms of what the what your kind of infrastructure needs to do. Speed is important, reliability targets, availability, also loading. Now, I've called it internal loading, and what I mean by that is just the physical loading, the train loading on the track, which goes into the structure, for example. External is climate, for example. So we all know in hot weather, well, we got hot weather, cold weather. As a track engineer, and certainly in maintenance, you just can't enjoy any time of year because it's likely to catch you out one way or the other. But ultimately, and of course, acid behavior is very important, and the deterioration rates, the mechanisms, the rates of deterioration, and constraints, as I said. So there's the environment, and in the UK, I think from memory, HS1 phase 1 environmental statement was 50,000 pages. So, which probably is a slight, I'm sure there's irony in there somewhere in terms of trees that we use, but it's about 50,000 pages. So, but the environmental aspect is very important. Population density, as I said, and of course, political influence. There were places, a lot of HS2 is down in cuttings, deep cuttings, and it's nothing to do with the engineering. And I'll just leave it at that. There was pressure put on, I think, I can't say this, especially as I'm being recorded, so I'll kind of won't say anything. So I won't mention any names. So, and these, of course, are especially important for high-speed, high-capacity railway. But of course, with Network Rail, we know all about high-capacity railways. So we run a lot of trains. Right, so I've got on to deterioration mechanisms. So wheel rail interface. So the wheel rail interface is a key aspect of system design. Now, I've referenced Mark Burstow. This is Mark Burstow, who was one of, as I said before, in the UK, we do certain things, we don't do certain things well. In fact, there's a lot of things I don't think we do well in terms of railway engineering, but there are also certain things we do very well, and wheel rail interface is one of them. Mark is one of the, he's an industry recognized expert in this, and Sinsin is also extremely good at this discipline. So forces on the track system. I'm not going to read that out, but ultimately, if you remember your O-level physics, energy cannot be created or destroyed, only transferred from one form to the other. So, and I'm sure most of you have heard the analogy, well, it's not the analogy, the size of the contact patch between the wheel and the rail is the size of a 5p piece. And therefore, that energy has to go somewhere. And on the diagram there, you can see the various deterioration or failure modes, and it affects the wheel. It affects the rail. Well, it affects the wheels, affects the rails, it affects the fastenings, affects the sleepers. In some form or other, as I said. And we've got to try and transmit that loading as efficiently as possible into the ground, in effect. And even the ground can be very, very difficult for high-speed ground trains, because you've got a phenomenon called Rayleigh waves and critical track velocity, which is one of the slides I haven't put in, but I can talk about it if anyone wants. So how do we mitigate that? So because ultimately, with the wheel rail interface, you're trying to control the performance of the infrastructure and the trains for that matter. Just as an aside, in terms of rolling stock, remember I just said in Japan, my kind of observation was that they put a lot of technology into the rolling stock. You're all familiar with some of the very long nose trains, okay, in Japan, the Shinkansen. Now, they're all different depending on the company. Well, those long noses are there because of the tunnels, because they've increased their speeds over the years. So the kind of Tokaido Shinkansen opened in 1964, for example, and that's 59 this year. I know because I was born that year. And that started off, I think, maybe 200 kilometers an hour. It's now running at 285. They cannot squeeze any more out of it. And clearly, with all the tunnels, they cannot increase the size of the tunnels without huge cost. So what they've done is they've really developed the rolling stock and the aerodynamics, if you like, But ultimately, what they told us that their rolling stock is it's got an 18-year design life in terms of the frame, the stresses that it's, subjected to at these higher speeds through tunnels which were not designed for those speeds. And basically, they replaced them after 15 years. So, I mean, that's just an example of, to us, a 15-year replacement of rolling stock. We've got rolling stock out there that's, well, from how long ago? So deterioration is very important. This one here is about millimeters matter. So again, the wheel rail interface. And what I've got down in the bottom right there is basically the difference between a P12 and a P8 profile. Now, P12 profiles have been around for quite some time now. And basically, I remember on the West Coast when I was at HQ, I was working with Mark and Simpson, and we were looking at the Pendolinos and some of the issues they had, and we were trying to convince the operators in terms of moving to a P12, and eventually they did, because they saw that they could actually, it increased the intervals between their wheel turning, which actually was a benefit to them. It saved them money, so eventually they did. But now I did this slide for civil engineers. I spent a lot of my 8 years in a high-speed 2 trying to explain to non-railway underlined civil engineers that millimeters matter. It's really important in railways. And to be fair to them, because a lot of them, if they're from a highways background or they're not from the railways, they don't quite get that. So I did this slide and I coined the phrase millimeters matter. And there was a professor called Rod Smith, some of you might have come across, who was a bit of a character, and he really liked this. But it was really important to try and get across to kind of people that millimeters, sub-millimeters matter. Between a P8 and a P12, it's sub-millimeter difference. Yeah, it makes in terms of size, but it makes a huge difference in terms of the wheel rail interface. So at high speeds, wheel rail contact conditions have a significant impact on the operations of the system, if you like. The wheel transfer areas in S&C are particularly sensitive. Now, this is not just high speed. There are significant increase in impact forces through S&C, as you can imagine. And one of the mistakes I think we made, and it's just, I can't believe how dumb we've been, we brought in explosive depth hardening. Personally, I think that's a nonsense, because there was a crossing in particular near Birmingham, I think it was, and it was banging. It was banging so loud that the maintainer called out Mark and Company, and Simpson, I think it was. And what they found when they measured it with the mini prof was that it was 1 millimeter out of tolerance, 1 millimeter. But because it was explosive depth hardened, it was bloody difficult. It wouldn't wear in, and they found it very difficult to grind. So that's an example where, explosive depth hardened, it might sound like a good idea. Oh, let's make it really hard, without actually thinking about the rest of the system. So millimeters matter. Right, so what can we do to improve the performance of the infrastructure? So again, this is just better reliability and resilience. Okay, so demanding operating conditions and high reliability targets at lower costs may require relaxing standards or new technology. Now, that's not high-speed 2, that's us now in Network Rail. That's where we are right now. We need to do things more efficiently. We need to do them better because we have less money and we have stringent targets. The operators are going to say, it's okay, Network Rail, if you want to delay us a bit more, it's not going to happen, clearly. So we need to do something. And that really simple graphic is, so proven technology, research and innovation. And at the research and innovation end, there's a bit more risk because we know there's risk attached to doing something new, something different. But benefits potentially far outweigh the benefits, because we won't get any more benefit if we just stay with proven technology. If we use research, innovation, challenge standards, whatever it is, we will get the benefits will be far greater than the risk. So, and again, we were just talking about, I had a meeting about innovation today about composite materials for the stovepipes, composite materials for the SPS, small parts. That's it. Absolutely. Okay. Okay. And so we were talking about this, and so the process is we have a theory or a model, then we do lab testing, and that's quite important. But it really depends what it is, clearly. The more complex it is or the higher risk it is, the more testing you probably need to do. Fastenings, for example, I know you've got Pandrel on your shirt there in terms of, well, you must know all about testing of fastenings. There's umpteen standards in terms of testing of fastenings, before you can introduce something. In situ trials is the next thing, because we need to trial it, get it in track. And again, another thing we're not good at is trials and trial certificates. We sometimes tend to, so we make it very difficult for suppliers. You ask any supplier, what's the most frustrating thing about Network Rail? And they probably all say, well, they'll probably give you a long list, but the first thing is always product acceptance, and that's because we're not good at managing it, because we don't think about what are the risks and how we control them. Instead, they sense that, well, put it in for 5 years, and if it doesn't fail, well, then we're okay. But that means 5 years you can't do anything with it. So we got to be a lot more sharp, focused in terms of the outcomes. And of course, operations. So that leads into, and of course, so the other thing I've got there is universities. So the front end of that, I think we need better relationships with our universities. And if you look at what we've got on Eastern region, so we've got York here, we got Sheffield, not so far away, we got Leeds University, Huddersfield University, who are the specialists in wheel rail interfaces. Nottingham University is on this patch. So we have Newcastle University. I'm not sure how railway orientated that is, but we have a lot of railway orientated universities on our patch. So, and with that, leading into that, so one of my bugbears, beware the vagaries of computing or computer modeling. Can we believe everything we're told? Well, I would say not. And a quote I've got there: our models tell us we can reduce ballast depths, we can reduce translation lengths, we can save millions. Where's your evidence? Oh, my computer, bop, 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 and out pops the answer. That's nonsense, quite frankly. And the thing about, I think one of the things I've seen it, and I've seen it again with some big name consultancies that have done modeling for us. And one of them, I sat on the steering group for the T1076 RSSB research, which is research into track loading. So going back to what I said about track system design, and one of the big name consultancies, it doesn't matter who, but one of the big names, they had on their tender, and we will use LS-DYNA, which is a finite element analysis package, to validate Vampire, right, which is the VR multi-body simulation package. It can't do it. A finite element, analysis package cannot validate a multi-body simulation. It can't do it. I think one of the problems is that computers have gotten so powerful now. Anyone with a laptop can, or in a company can download a model or a package and come out. And within Network Rail, we've done it in the past. So now some of the older generation, Richard, you can't see this, but you might recognize it. Does you can, okay. Does anyone recognize that? It's from the Hitchhiker's Guide to the Galaxy. Now, I know the younger generation won't do it because this was a brilliant book and a pretty good BBC series, to be fair. So that was a supercomputer called Deep Thought. Okay, that's what it was called. And they asked it, basically, they basically wanted to know the answer to the ultimate question of life, the universe, and everything. And they put it into this supercomputer, and it took eons. I think it took thousands of billions of years, and it came out with the answer. Does anyone remember what it was? 42. So for those of you younger generation, you probably won't get that. But the irony is there. It's absolutely spot on in terms of 42. There you go. After billions of years of the supercomputing, that's what it got. So it's just a plea really to just challenge, going back to challenge. Just because someone that has a flashy computer or a flashy computer, but a program with nice color graphs says something to you, doesn't mean it's true. And with ballast in particular, and I'll come back to this later, ballast, it's the most inhomogeneous random material, even soil mechanics. So when you do, earthworks has more uniformity than ballast. So when people say, well, I can model ballast, now there are ways to do it, but it's not a finite element analysis package which actually creates a mesh. So rant over, or maybe it's not. So it's important that, so in my view, that's another reason why we need to get close to academia. So we can work with them, because they have a far better understanding of the limitations as well as the capabilities of kind of what their modelling can do. So another one of my things, I did a talk to WSP graduates a few years ago, and this kind of just so this photograph kind of didn't kind of, I just got blank looks, and I should have realised, well, it's from the 60s, so and so forth. So what I did so in case you don't know, this is Scotty from Star Trek, and his famous expression was, "You cannot change the laws of physics, Jim." And I just thought that's a great expression. You cannot change the laws of physics. So high-speed rail, conventional rail, doesn't matter. The laws of physics don't change, unless you're in France. I have noticed that, because the vertical curves are bloody odd, and their bridge designs in HS2 are just unbelievable. But broadly speaking, I think the laws of physics don't change. So for those younger generations, this is the current one, which is Simon Pegg. And the only quote I could find is, "Do they have sandwiches in the future?" Which hasn't got quite the same ring to it. So anyway, so high speed, so track requirements. So high speed and then versus conventional. Well, in the high speed arena, a dedicated passenger line is better because, as I said, the tolerances are far tighter. And I'll come on to that. Good vehicle track interaction, especially with classic compatible trains, because the first trains are going to be classic compatibles. They're going to run at 360 kilometers or 330 kilometers, whatever it is in high speed 2, and then they're going to trundle off onto the west coast at 125 or whatever that trundling speed is. So that's really important because they're two very different, because the HS2 infrastructure and trains will be designed for, well, trains will be designed for that infrastructure. They also have to try and design them for network rail infrastructure, which is not easy. Track alignment, suitable for high speed operations, and I'll come back to that. Track form, I'll come back to that as well. Consistent support platform as well. And what is the track founded on? And I love saying to railway civil engineers or structures engineers, the sole purpose of your structure is to support the track. It doesn't have any other role in life. Now, take that with a pinch of salt, but anyway. So track bridge interaction is another big one. Track bridge interaction is really important. Going back to what I said about a small country, there's lots of things to bridge. I think it was on the news, the Colne Valley Viaduct is 3.5 kilometers long, just outside the M25, I think it is, and it's curvy. So, so we got very strict, so high speed, you got very strict tolerances for geometry, dimensions, wheel rail profiles, both during construction and maintenance. And by virtue, and as well, just got to think about it as well. So running at 140, can't remember how many kilometers an hour is that, 250-ish?
225.
225, okay. Okay, good enough. I'll come back to that as well. And control, so critical track velocity, which I'm not going to cover, but which basically Rayleigh waves. So which if someone wants to know, I can go into details of what they are in terms of critical track velocity, but it's an issue potentially for high-speed trains, but not just high-speed trains. Gravel Hole on West Coast has critical track velocity issues. The Fens, Silton Fens, I think it is, in is it Anglia or East Coast? Can't remember where. Peterborough. So it's not just for. Excellent. Right. So the key thing with high speed, well, with a new rail, is to focus on an integrated system design. So, and I'm just going to quickly go through this. So, in terms of designing your track form, the mechanical behavior of the track is really important. So there's higher dynamic loads, as you would expect, higher vibration levels, you know, in the rolling stock and the superstructure elements. So, which leads to fatigue and wear, going back to the, you know, deterioration model. Higher stresses on the track bed. Think 140 miles an hour, because I've seen a report and said, oh, we don't think you need to do that with the track bed if you're on to 140. I think you would, actually. It's also about optimizing track stiffness. We do not do track stiffness well in the UK. We just don't do it. We have the values we have, I don't think really, we haven't really defined what our track stiffness is. And it's a mishmash of, I mean, certain people in the past have even talked about, and I think it was mentioned here, our next speaker, about stiffness of ballast. Well, actually, stiffness of ballast is not specified and is not measured, or shouldn't be. There's no point. It's not about stiffness of ballast. It's actually about the consolidation. Because no matter how stiff or not stiff it is, actually, you don't want it to move once you put your track down or once you put your rails in place. So, so the case study I'm going to use, how long have I got left? Half past?
Yes, we probably it's half hour.
Okay, half past. Right, so I spent 5 years doing this, and there might have been Richard there in the background. A few people, I can't remember if it was Richard or not, but some said, you'll never convince McNaughton to go with slab track. And the point is, I didn't set out to convince anyone to go slab. We did a lot of analysis, and we put the evidence together, and it became clear what the answer was. That's the point. It's not about having an opinion. It's about actually going through, developing your data, developing your evidence, and actually looking. So providing what you've done and you do it properly, it should actually inform the, inform the choice. So what we did do was develop an evaluation process, which is quite good, because around the world, there tends not to be a track form evaluation process. Just France and Spain go with ballast. In Asia, they tend to go with slab track. They tend to go, Germany tends to go with slab track now as well. So they tend to go with what they know. But we developed this. So what we did was we got Sistra / SNCF to do a statistical analysis of their TGV network. Now, at that point, it's increased since then. This is about 2014, 2015. There was 6 routes. Okay, so the first one, Paris-Lyon, LN1, and LN6 was the last one, which is the Paris to Strasbourg line, and that's the line that they broke the world speed record. It's 574.6 kilometers an hour or something like that. But what the French have done is they have evolved their kind of knowledge and their standards as they go. So what they specified for LN1, which was in the 80s, is very different to what they did for LN6, which is what you'd expect, because they've learned from the problems they have. So what they did was they basically did a statistical analysis, and they looked at their maintenance databases, and they broke up all these routes into speed, speed, and then they looked at the tonnage, basically, and they came up with a graph here. And this graph said, based on so if we applied airspeed and tonnage for HS2, which was 360 kilometers an hour, could be 330 operational speed, doesn't really make much of a difference, but it's the tonnage, it's the number of trains, that's the key thing. So 18 trains an hour worked out something like between 65 million gross ton per annum. On LN6, their annual tonnage is about 11. So if you look at the difference, over 5 times, over 6 times more than that. And their graph told us we'd be tamping the whole route 9 times a year if we did, the whole HS2 route 9 times a year. Now, clearly that wasn't acceptable. So then what we have to look at, how do we optimize the track system? So they've started looking at undersleeper pads and bitumen asphalt sub-ballast, and I'll come on to that later. So, but what they didn't have was enough knowledge or evidence of undersleeper pads. So we went to, as I said earlier, the Technical University of Graz, to Peter Veit, and he did an analysis, because Austria, I think, probably lead the way. In my opinion, Austria and Switzerland probably lead the way, I think, in broad terms, in terms of track practice anyway. And so Peter Veit as a university, I think even then, for the 15 years, he got a download of all the Austrian railways track quality for the whole route 4 times a year to do it what he wanted. So he had loads of data to play with. And basically, they now use undersleeper pads with everything. And ultimately, he was able to give us a reduction factor if we were to apply undersleeper pads. And the other thing was absolute base tamping, the French call it, which in our world is absolute track geometry. So you don't just tamp things, you actually go survey design, and then you implement a design tamp. And if you do it like that, even with all that, on the best day, I haven't put the numbers on the left, but we basically got it down to, we'd still be tamping about 1.5 times a year, the whole route 1.5 times a year for that speed and tonnage. That's the key thing, because those graphs there, so the bottom one is 10 million gross ton, 20, 30, 40. So we had a graph then that we could use, and it's the key input into our whole life cost analysis. And ultimately, so the key thing about this is it's the cumulative tonnage. That's the killer, right? Not so much the speed, as you say. The speed has some sort of influence, but it's the tonnage. And the higher the tonnage, more tamping. when you tamp, you reduce the ballast life because it's controlled demolition, I think, from day one, tamping. And basically, the French work on 25 tamps for high-speed railway as a rule of thumb before you have to renew the ballast. But that was good enough for us to have, to work out whole life cost analysis. And of course, if we're tamping it a lot, well, then we're going to renew it a lot. And all of a sudden, we could demonstrate that slab track was potentially a really good solution in terms of whole life cost. Now, the rudder, what really made it fly was the construction guys, my counterparts in production. If you're building a railway like ours, and especially with lots of bridges, when you're laying ballast, you have to do it linearly. So you have your access point, your railhead, and you have to work away. You can work away in both directions, but if there's no bridge, that's been handed over. If there's a big gap where a bridge is being built, you have to stop because your methodology is big track renewal trains. With slab track delivered by road, you can go in and do it anywhere. And the guys worked out 5 kilometer kind of sections and how they would lay the tracks. So the construction played a big part in the decision as well. So right, I better crack on. Right, bit about slab track engineer design. This is really important. If Liam Jackson is on, I apologise because I was supposed to write the kind of slab track section in 2.02. The draft I saw started off, slab track's good for bridging poor soil. It's not. It's just wrong. It's exactly the opposite. It is not there to do that. It's based on pavement engineering. Okay, pavement engineering is built up on layered stiffness, and that's why most slab track or track slabs have only have reinforcement around the neutral axis. There is an exception to that, and I'll cover that in a bit. But ultimately, BSEN 16432, which is the slab track standard, is based on pavement engineering. It's the German kind of, it was developed in the TUM, Technical University of Munich. And of course, the UK, if you remember PackTrack, P stands for pavement because it was laid with a paver. So, I mean, like everything, the UK was brilliant initially. Tilting trains, we had first slab track. We have a lot of legacy of actually being innovative. I would argue we need to get back to that. So anyway, slab track design, it can be engineered, it can be modelled, controlled stiffness and rail deflection, 60-year plus design life with minimal maintenance. And I remember being challenged, after 60 years, you have to renew it, you have to put that into the cost. No, reinforced concrete is not suddenly going to crumble and turn into ballast after 60 years. So what would we have to do? Actually, we might have to increase the maintenance. So we might have to do minor concrete repairs, if you will. So therefore, that's how we work that out. Oh, so just one thing there. Slab track, by the way, is normally 2 slabs. You have the track slab itself, and you normally have a base slab of some description. So it's not just one; it's usually 2 layers, and it depends on design. It can be more. So slab track and earthworks. This is one of the biggest risks, especially if you build new earthworks. If you dig deep cuttings and it's in clay, you potentially get heave problems, and heave lasts for a long time, potentially long time over. You will get heave. If it's an embankment, you get settlement. And a big discussion is when you start to install slab track. And there's a process which I sit on an ISO group now, but it's an unofficial process that they use in Germany. And basically, you have to monitor the settlement. So if you're talking brand new earthworks now, high earthworks, 40 meters high, there's such a volume of soil there. No matter how much you compact it, and the ground is sat on, it'll settle and settle with time. And that graph there is supposed to show that you actually plot the settlement, you measure it, and then when you're pretty confident that it's tailing off, then you decide to install your slab track. Because the last thing you want to do is install slab track and then it moves because you won't get your rail levels height. You'll always have to adjust the rails somewhat. And the other thing about slab track on curves, the top of the earthworks has an apex shape, but around curves, what we wanted to do is actually, if you think these are like sleepers canted around curves, you have that Z or W type shape, and it's really important. You can see the yellow there. it's really important that that the track contractor understands that they have to come along and take an earthworks that's finished by the civils like that and make it into like that. So settlement mitigation. Now, apologies, but I don't have a plan for fasting on there. They weren't around, and I know John Porrell well, so I would imagine. So yeah. So anyway, but one of the kind of original slab track fastenings was the Voslo 300 system, and the key point with that is it can actually be shimmed. And if anyone has ever maintained longitudinal timbers or way beams, it's exactly the same principle. Hopefully, it's a bit more high tech, but basically the same principle. If you have a base plate, and I remember being out on site doing a scheme as a tech and putting kind of plywood packings underneath. These aren't plywood, clearly. They're kind of steel plates, but ultimately it's the same principle and it can be done. And for heave, one of the things we were looking at where we know we're going to have heave, we were thinking about we will put packings in before. So when we install the tracks, we can take them out all the time. But the point is you can adjust rail levels with slab track. So, I mean, there are other ways as well. You can jack the slabs, you can jack the slabs up as well, or you can cut them off, jack them up and then regrout them. But in theory, clearly that you don't want to do that. Right, modern earthworks designs, and this leads me to, so modern earthworks, I'll put modern earth because it's the same for new build, but in high speed in particular. If you're building a new embankment, it works on a layered stiffness approach because where you want your stiffness is underneath the track. That's where you want your stiffness. Because the stiffened material is normally more expensive, higher specification, more expensive. You don't need it down the bottom of a 30-meter embankment. So therefore, you tend to have this this kind of layered stiffness approach. So underneath the track, it doesn't matter slab or ballast, you have a sub-ballast layer, a protection layer. It's normally compacted granular fill, and I've got up there the EV2 values. So it's normally EV2 value of 120 megapascals. That's the same in Germany, France, Spain. It's all the same. It doesn't vary. The interesting thing is the layer below, the prepared subgrade. The layer below is actually stiffer for ballast because the slab track system, the superstructure is stiffer, so you don't have to have a stiff as a layer below. So it's potentially slightly cheaper. And what I put up there on top right, I got this from Wolfgang Vogel, who was the guru in Germany. He's long retired now. He's in the 70s. In terms of he did a lot of work, well, in the 70s, they measured, and this is about the pressure. And if you see the far left where it has I or 1, that is slab track. So along the top is the force or the pressure, if you like, and that's the depth on the left. And you can see that slab track is, so it doesn't go very far to the right because because it's got a very different, it transmits the loading in a different way. Slab track on bridges and viaducts, really important. Bridges move, long bridges move. I made the point earlier on, hitch and viaduct or hitch and flyover. We built that maybe 10 years ago now. It's got 3 rail expansion devices on it. I reckon it only needs 1. I think we've done too many. So bridges move, they expand and contract. The longer the length of the deck, the longer or larger the kind of movement, if you like. So that's not new, but what is new is our use of rail expansion devices, sometimes called structural expansion devices. I personally don't like that because I think a structural expansion joint is the bridge joint that kind of moves, whereas these things, and on the far right you can see where the gap moves, and some of these can be up to 1200 mil. They've got these suspended frames which they put sleepers on basically, and when they close, so they can close up like the bottom left or they can open out, and this one has 2 sleepers in effect. So so right now I've got a load on that I was going to put in, but I haven't. So track renewals implications. So with slab track, one of the benefits is maintenance is more about rail management. If you've done everything right, it should be rail management. Still have to grind it, still have to ultrasonically test it, still have to change the pads as we would, but it's rail management, no tampering, clearly. And for S&C it's the same. If you want to change S&C, change the ironwork, not the slab itself. On the right, and again, worked with a guy from JR West who was doing a master's in Southampton University, and he gave me this, and he said in Japan they actually change up to 5 of their slabs per night. And you might ask, right, why do they change them? this is in a tunnel underneath the sea, so it's basically saline corrosion. So that's why they're changing them. But they've got it to a stage where they can change 5 of their precast slabs a night, which is pretty good. So the point is, you can renew slab track, so you can change it. And this is just about, again, I had to do safety as well. And I think down the bottom, my key, so precast slab tracks made in factories, which is safer anyway. I think they're kind of machine. You install them with machines. There's very little manual work apart from guiding and kind of tightening up. But the key point is down the bottom. If you've less maintenance, one of the best ways to have a safer environment for our staff is not to have to go out onto the track. So if you don't have to go out onto the track to maintain something, it's inherently safer for our people. So, and again, this is just about the different types of slab track. And since I did this, the one second from right, precast slab OBB pour, that's the slab track that was chosen by HS2. So that's the slab track. And we've just put that in King's Cross remodeling. We just put the OBB slab track in there last year, I think it was, or the year before now. So, and we've also got resilient slab tracks and tunnels. So the top one is LVT or Sonneville. We have that in Canal Tunnel, I think it is, at St. Pancras, for example. So we're already starting to use these. And the bottom one, Setibet, we have this high-speed one. So that's a photograph of high-speed. So we're already starting to use slab track in the UK. But where you have slab track, you also have transitions back onto balsa track, and these potentially are an issue. So with kind of transitions, you got 2 aspects. There's the elasticity, so there's the stiffness, difference in stiffness, but there's also the plastic settlement, because if you have something that's rigid and you've got kind of earthworks, I mean, the run-ons and run-offs to bridges, even with ballasted track, it's a similar sort of thing. You know, when you get slacks off the end of the bridges, because the Victorian earthworks are settling. But with a design, hopefully we can design that out, but it doesn't always work. Can I just, in terms of stiffness, can I have a show of hands? So who thinks, I've got to, right, in terms of stiffness, which is stiffer? And I'm going to ask slab or ballast. So which is the stiffer track form? Okay, hands up, slab track. Okay, and hands up for ballasted track. You're right. It is, but going back to designed, so designed with 120. So basically, slab track. It depends how you define track stiffness. And while most people or most infrastructure managers define it as basically rail deflection under loading, basically. So it's the rail deflection, and that rail deflection is influenced by the layers underneath. But slab track is actually the kind of normal value that they work to in slab track design is 65 kilonewtons per millimeter, whereas ballast is 80 to 100. Now, our ballast track may not be that stiff, but certainly a brand new high-speed ballast track will be stiffer. So, and people kind of, it's not intuitive in one way. So, right, I'm going to go on to ballasted track now. This photograph, I've seen this used in the PWI, but this is from Austria. And the key thing about this ballasted track is that you have the layer underneath the ballast. This is a sub-ballast layer. And I cracked a joke earlier on. Anyone who thinks it's a good idea to put sand underneath ballast, leave the room now, please. We're currently working with SNCF to actually look at this method of doing unintrusive investigation of the track bed, Pandascope it's called. And they could not get their heads around that we put sand on the ballast. They just could not get their head around it. And so what the norm is by far is some sort of compact granular fill that basically stiffens the subgrade below, because that's generally the point of it, is to increase the stiffness. So this is what, so ballasted track optimization. Now this is my opinion, okay? Rails, right? We can improve the rails, railhead profile, metallurgy, sleepers, shape, material, behavior under loading, really important. Dynamic design rather than just G44s were designed for 30-ton axles. They weren't designed dynamically. Did a lot of work with OBB in Austria, and they said it's very important for a sleeper to kind of narrow in the middle, because if it's straight like an S&C bearer, it's too rigid. And if you've ever seen ballast flow, so on high canter track on West Coast, for example, it's not just there, the ballast flows to the low rail. And one of the reasons for that potentially is the rigidity of the sleeper is too rigid. So the shape of the sleeper is really important. And if you look at old sleepers, you'll see a narrowing in the center. So, and of course, you have the width underneath the rail seat, which is where you want it, because that's where you want to spread the load. Under sleeper pads, these are not new anymore, but they're a really good thing. But I get with minimum viable product, under sleeper pads is not necessarily something that we're going to be able to afford, but it could be. And I would suggest again, if we're running 140, that's something we should consider. Ballast. Now, I love this. For HS2, now, given it's the middle of the Six Nations, I love saying this. When we looked at ballast, we found that English ballast isn't hard enough for high-speed rail. I'm not kidding. There's no quarries in England with ballast hard enough for high-speed rail. And HS1, or CTRL as it was, Section 2, had to go to Norway for their ballast. We were going to, I don't know where, well, we're not going to be ballast, but we were looking at Glensanda in Scotland. So, as I said, so one of the key things about ballast for high speed is the Los Angeles coefficient, which is in effect the hardness of the stone. And I remember meeting a guy once from Tarmac Aggregates, and he said something I'll never forget. He said, you cannot change the inherent properties of the stone. So granite is not granite, or granite doesn't equal granite equals granite. Granite from over there is different to granite from over there. You can change mechanical properties of how you break it up, how you shape it, but the inherent kind of hardness of the stone itself, the content of the stone, you can't change. LA coefficient is quite important. Washed, right, with fines, without fines, which is, I think, what we get. I've just seen a safety notice, a safety bulletin about ballast and, you know, the dust. We don't wash the bloody stuff. It's just what we get out is just shocking. I know how they do it. The most important thing, in my view, ballast must be installed in layers with a DTS. None of this rubbish of using triple whacker plates and putting it down in one go and thinking it's, oh, that's good. It's not. Ballast is not a compactable material. Okay, if you look up the civil engineering dictionary definition of compaction, you will find the actual grading of the particles. You will find moisture content. Do we do the moisture content of ballast when we whack the knife out? Of course we don't. So a DTS, the key thing with a DTS is it oscillates from side to side. So my analogy, you have a pasta jar at home with dried pasta spirals, and you go to the supermarket and buy a new plastic bag full of pasta spirals. And when you pour it into your pasta jar, the top will go like that in a peak, and you can't put the lid on. Do you A, go like, put the lid on, or do you B, shake it from side to side? That's what a DTS does, shakes from side to side. So QED, as they say. And the on the right there is the Spanish. This is actually, and I've done this on West Coast. I've actually done it in reballasting. They basically put the track skeleton, rails and sleepers on the ground or on a small layer of ballast, and they basically flood it with ballast on top of it. Sorry, on the formation, not on ballast. And then they basically flood it with ballast, and you get an old 07 tamper and hike it up as far as it'll go. Then you put the DTS and you DTS it down, and then you repeat. Drop more ballast, hike it up, DTS it down. And what you do is you build it up in stages, and it's completely consolidated. And all over Europe, that's how they do it. And certainly for high speed, but they do it in conventional rail. One last thing is people also think, you know, we think of a pyramid in terms of loading. It's actually not potentially. This was done by French SNCF. If you think the randomness of ballast, it's more like the localized rigid structures, they call them. It'll find its load path depending on the randomness of the ballast, if that makes sense. So it won't be a uniform, and that potentially increases the stresses underneath as well, because stress is force divided by area. If the area is smaller, you increase the stress. Right, I'm looking at the time now. Sub ballast, bitumen asphalt, brilliant. Bitumen asphalt is a fantastic sub ballast, right? Down the bottom is from, basically the picture bottom left is from Austria. Build a road first. What do you even think about putting a track and build a road? Okay, it's uniform, it's got all sorts of advantages, it's got better durability, it's better. And on the right, what you've got on the right, the top is SDs for LN6, and the right hand one is actually with bitumen asphalt. The bottom two are two lines on LN6, and this is running at 320. And the bit between the two vertical bars is, it said zone avec GB. That means bitumen asphalt. And you can see those bars are the tamping, the number of tamps. And you can see that there are less tamps when we have bitumen asphalt as a sub ballast. It's fantastic. And this is a photograph from a friend of mine, Mark Cunningham, who now works for WSP, that he took on the Nîmes to Montpellier line. And you can see, so there's a number of things going on here. You can see the road. You can see the sleepers on the right. What they're doing there is they're laying the first layer of ballast with a paving machine. And you can see just behind it is a tipper truck, right? Tipper truck just tipping ballast. But the key point is there, and those of you who've been around a while and remember expressions like center bound, they've got a groove. Can you see the groove in the middle? So when they come to lay the sleepers on the unconsolidated ballast, they're not going to center bind it. They're not going to become center bound. So they put a groove. And there was an old codger called Graham Bernard, who retired a few years ago, who said to me, and he reckons the only reason we brought in whacker plates was to actually give to give a smooth surface before we put the sleepers on, not actually to compact ballast. So anecdotal, I know. But anyway, and of course the last thing is just to the left of the lorry, you can see the big ballast mountain there as well. So to me, that's a fabulous kind of photograph. And this is my ideal track. I took this photograph, my ideal track for ballasted track. 1060 rails, ballast laid in layers with a DTS, sleepers with under sleeper pad. But look at it. So down the bottom, you've got the bitumen asphalt sub ballast. And above that, you've actually got this troughing route. And if you look at the troughing route, it actually acts as a retaining wall to the ballast. So you've got the lateral stability. But now the University of Southampton research, Track to the Future, Traction 1, has actually demonstrated that lateral restraint to ballast will actually reduce vertical settlement as well. It's a key outcome, and that kind of does it. I know I'm getting close, Ben, so I'm just going to flip past that. Right, track. I'm going to go through this really quickly. Give me another 5 minutes. Right, high-speed track alignment. The aim of high-speed track alignment should be to basically lead to good vehicle dynamic behavior. In terms of track alignment design, you should always be thinking about what is the train doing, what is it seeing, and therefore you want long, flat geometrical elements, certainly in high speed. The bottom line is the bottom photograph on the right is a view from the Cologne to Frankfurt high-speed line, which is actually 4% gradients, which is phenomenal. HS2 track alignment design is cognizance of other high-speed standards and the balance between the physical, as I said, the constraints. So optimum design is not found in the TSI, and the ultimate objective is to design a safe, reliable, and efficient railway. Good design is normally a compliant design, but a merely compliant design is not necessarily a good design because of the subjectivity of track alignment. Track alignment modeling combined vertical horizontal curves. All I'm going to say on that is that you have to think of both. You must consider what's happening vertically as well as horizontally. Okay. S&C. That's a photograph from Taiwan, I think, and that's only 160 km/h turnout, I think, but being brought to kind of site. They had to take down traffic lights. I think Mike Baxter will remember that. I know Mike's online. So switches and crossings, high speed, clearly swing those crossings on straight track. You've got different types of geometries. Intersecting is 113 pounds turnouts, as we know, is intersection geometry. When I stand up, if you stand up before you go to a turnout or a divergent route, you'll be thrown over. Tangential is the other one, but which is basically they're kind of in line with the true line. But non-intersecting is basically used the clot-eyed, and with high speed 2, we went for the German geometry in terms of clot-eye design, because in plain line track alignment, you always put a transition before a straight into a curve. But in S&C, and I know why we do it in S&C, it's a safe space in stations. You don't have, but for high speed, well, actually, it's a good thing to do, and it reduces the jerk or the jolt. This was Euston, and it was a very complex station. And basically, we had we had to do I put a minimum standard of 400-meter radius turnouts, so we wouldn't get 053 failures basically, and to fit it into that layout was difficult, but we did it. So I'm coming to the end, Ben. So just to recap on what we're doing, so this whole point, what I've shown is demonstrate some of the things that we've done in HS2, but it's not about HS2. It's about we as engineers. I think, to me, it's about thinking critically, evaluating, deciding to innovate, engineer, basically. Ultimately, engineering is a series of trade-offs. People say, oh, lowest whole life costs. We're not in that world anymore, lowest whole life costs. We should do a whole life cost analysis, but it may well be that a slightly lower or a slightly higher whole life cost for a far lower capital cost now is, a suitable outcome. I'm not going to do that. So I'll end up with Scotty as well. So back to Scotty. We should be challenging standards, understand the engineering principles, know the rationale behind the specific clauses, requirements, and standards. That's the key thing. If there's a requirement in there, what's it in there for? Why is it in there? Understand the risks that are being controlled, and then you can evaluate the impact of actually changing a specific requirement or parameter limit. Be numerous as well. Don't just say, oh, I can't do it or it costs too much. You have to be numerous. Thank you for listening. On a bit longer.
Great, thank you. Questions for Niall? Online.
Right, shock. Yes.
You started off your excellent, isn't it? Very much. But you've highlighted throughout the piece, from the engineer is to be ingenious. Good comes from. And yet we have a culture which suppresses that engineering through the way that we manage the railway, certainly in the UK. Sure, you know how we change that so that we can unleash the abilities of engineers.
Right. Well, I think the first thing I'd say is I think we've got to get together as a community of engineers is the first thing, which is why we had the engineering conference on Eastern Region. It was to form a community, and I think it's to get these things out, on the open, because let's be honest, there's a lot of other pressures. So we have design managers in the design office who don't give a monkeys, quite frankly, about what the outcome is. They have a deliverable by a deadline, and they want the design out with the deliverables by a deadline. That's it. I think we've got to give air cover to people, to more junior engineers. So A is to have a conversation with them. I think we've got to give them air cover in terms of, and I've had many shall we say, robust conversation with project directors or design managers on that basis. And I even experienced one particular project director went and asked a graduate to do a track alignment design because he knew that their track alignment guys wouldn't do it, because he wanted to do it to kind of fit in some sort of civil kind of structure. And, so I think it's about community. It's about enforcing this message. There's also something about procurement in there as well. I think we've got, because, when we first on MML electrification, when we spoke to designers first, they were, well, look, our standard says to comply with the standards, and therefore we've given you a compliant design and the 2-second rule for vertical kind of alignment, which is wrong as well. That's just nonsense, but that's been now sorted. The standard's been changed. So I think we can help by changing the standards, but we've got to get people thinking about it and giving them the air cover to kind of think, I think.
One thing you didn't mention when you were talking about ballast versus slow was, if you have ballasted traffic, all the extra infrastructure you need to park your engineering trains, unless you're getting 8-hour blockage, which you cannot have in the new railway. So there's a cost of that I think is quite significant.
It is, totally agree.
Save a lot in infrastructure.
Absolutely right. And because, well, basically you don't need a whole fleet of tampers or engineering trains for starters. You don't need the depots to stable them. The kind of you don't need kind of railheads to load materials. So, and HS2 did actually, I think they, as I said, it's very political, as you're very aware. I think they started off with, we need this size because it could be ballast. It was only when it was confirmed that it was slab that they actually shrunk it down to kind of get the savings. But you're absolutely right. I mean, I'm not saying a slab track is the right answer for everywhere, but it's certainly, I mean, we're now using more of it, you know, in the conventional railway. I think we're still very nervous of it. I think we still know very little about it. There's only one or two companies you trust to actually design and install it in the UK. You know, there's a lot I wouldn't trust, you know, to do it, quite frankly. And but as I said, it's yeah, I do think it's the key thing with this is we did all the analysis and we presented the evidence, and the fact it got through, you know, it got through McNaughton first, it got through then our various executive panels, and then it got through the DFT, BIS, I think, is Business Innovation Board or whatever it was. So, but yeah, that's absolutely right.
Yeah, my question.
So, question and challenge that the rail industry 18 years ago looking at self-healing rails metals and mechatronic train wheel sets and points at no moving parts or rails. Personally, think that HS2 should not have been developed as current rail technology. Need to for running interface and a conventional rail. So HS2 and 60 will be an innovation, not running more the same. What more are we doing to challenge, innovate, and change the norm? Also, that you can sell technology.
Okay, well, that's quite. So I would say the first thing about that is this is all about risk, isn't it? And there is a difficulty with using. It's all about, you've got to assess the risk in terms of what technology you're talking about. So, for example, and I'm going to use signaling and saldo. I think we had something like a 3-month overrun on one of the West Coast's route modifications with the signaling at one point. Because it wasn't developed enough. I know the underground, for example, didn't use moving block signaling technology. The point is, it's all about risk and the kind of technology readiness, if you will, and therefore so I would not be a fan of moving away from rails. We're not going to start using rubber rails, for example. In fact, if I may, and this is where innovation goes wrong, technology goes wrong. Eschete, I think, was the crash in Germany in the late 90s. It killed over 100 people. And what they did was they experimented. So they took a tram system where they took a steel wheel, and we normally have steel tires, and they put a rubber layer between the steel wheel and the steel tire because it had it in trams, because they were getting excessive vibrations. And of course, what happens? The steel tire fatigued and broke at high speed. So it's all about balancing risk, I think, with the actual readiness of the technology. So, sorry, I didn't ask a question.
In terms of the sort of 140 running on the East Coast Main Line proposals, what do you think is the discipline that's going to be most problematic in achieving it? Is it the trap head and works?
I wouldn't like to say it's one discipline. I just think we need to look at the whole thing as a system. So, but I think I've seen a report from 2014, and the authors of the report, or the originator of the report, the company worked for us in High Speed 2. And one of the first things I learned in High Speed 2 was no one in the UK had a lot of high speed experience. None of our consultants, because we just didn't, and because High Speed 1 was a French system, you know, bought off the shelf in effect. And so I think there isn't a lot of experience. We have more now, clearly, because it's nearly 10 years later. But I think, you know, one of the things that did say that report was, oh, we don't believe you'll need any kind of, you know, to do that on the track bed. They said, and, you know, they even mentioned you might need to remove pre-76 rail. And you kind of think 140, shouldn't it be 1060 as a minimum? I would have thought. So I think signaling is probably going to be okay because you got the digital program anyway. But I think so probably the track and civils then being, I mean, the other one was tunnels, you know, as well. And I'm not convinced they got that right, because going faster through tunnels. Because the other thing about 140, if you constrain the actual lengths that you can run at 140, it becomes not worth the cost. So I think you know you've got to try and get, because that's one of the things I've seen which I was quite surprised at. The lengths that they were hoping to run 10 billion to, to shave half a minute off a journey time isn't going to cut it, I think. So I think civil's definitely.
Possible level crossings as well.
Yeah, I don't think you'd have level crossings.
You have to look at those in, I think.
I think so. But I mean, that's all subject to analysis and.
No, we reissued 202 in December. What clauses are at the top of your hit list next time for us to?
Well, I know they've got.
got.
So in terms of track alignment, there was the 2-second rule. The 2-second rule was never meant to be for vertical alignment. So got hold of Jeff South, put it in, and Jeff said what, and he put it in. And what he said was he was trying to get designers not to put in, stupid designs. But of course, for those of you know, when you're trying to get under an overbridge in terms of track alignment, the standard was it must be a constant gradient and it must be 2 seconds long. So we were having to design this long gradient going down, and which is just a nonsense. The actual, there's nothing wrong with the vertical curve underneath the bridge. Once your drainage doesn't follow it, the drainage needs to keep going in a linear key. That's the key. But and the other one was the length as well. As I said, the 2 second, it doesn't need to be 2 seconds because the natural frequency of train suspensions, it's different horizontally than it is vertically. And the 2 second rule, I think, was initially put in for horizontally. I remember Jeff always telling me there was a ladder at Twyford, I think, on Great Western or something. I think it was around there. But when you kind of went through one crossover and then you went to the other one, it was quite rough because they were too close together in the context that the train hadn't stabilized before he went. But that's very different to, going through crossovers is very different to just trying to get down under a bridge. But I think we've got that now. But track stiffness, I think we need to do track stiffness. But the slab track, as I said, I was supposed to rewrite that and I never got around to it. So I apologize.
We just put you towards the your standards.
Yeah. Well, that's what we wanted. We've got that now. I'm sure I can think of a few more. Sorry, I wouldn't dare ban the use of whacker plates and putting ballast down because we're too far down that road now. But HS2 I did. I'd also ban cast crossings as well. Actually did it on HS2, banned cast crossings. Too many failure modes, they're just popping all over the place. So.
Okay, any more questions? Excellent.
Yeah,
So,
you started. Sorry, you started talking about the current financial and political climate, and then later on you said you wanted no 4% grades. But if you design a new railway with 4% grades, it'll be cheaper to build.
It would be cheaper to build, but it wouldn't be cheaper to run, I don't think. And I think the traction costs alone, I think, will be one of the. But I think it's a moot point because the TSI now mandates a maximum of 3.5%. So because that was done before, to be fair, I think it was done as an experiment because since then, all the routes they have in Germany. So the Cologne to Frankfurt one, after that was the Ingolstadt to Nuremberg, I think. And more recently, the one I was out on was the VD8. And they've got all ruling gradients of like 2% or something. So even the Germans have rolled back from, I think it was an experiment to follow the motorways. But I mean, it's got to be horses for courses. And again, I go back to risk, whether it's performance risk, cost risk. You've got to understand the risk in terms before you make a decision. Sorry.
Yep, and that decision has to be made both on a per design and a per system basis.
Great.
Thank you.
Okay. Thank you, Niall. So what did we learn? We learned that managers are dumb and engineers are smart.
Yep.
Millimeters matter. Beware computer modelling. World revolves around track. Ballast is stiffer than slab, depending on your definition. English ballast isn't hard enough.
Oh, I love that.
And next time I need to put pasta in a jar, I will know who to talk to. So
not as contentious as I would have thought.
So thanks, Niall, for a really interesting and thought-provoking talk this evening. If we can all say thank you in the usual manner. So next meeting back here on 16th of March for the second part of our controversial presenters series. thanks to the many people who joined online. We'll keep the meetings online, and if we're in this venue, I think it suits an online audience far better than what we've done before as well. For those in the room, if you could put your cups and glasses in the kitchen before we go, that would really help the cleaners. We're off to the York Tap if anyone's interested in joining us. And do we have a charity collection box?
Oh, it's, I can go and grab it very quickly. It's up on the third floor.
And there may be a charity collection box appearing soon, possibly at the pub. Okay, thanks all. Thanks, Niall.
You're welcome.
Thank you very much.
I sort of,